So the last experiment that we are going to demonstrate is related to the inverter chain design, and here we are going to demonstrate the importance of inserting these inverter chains or buffers in reducing the delay of the design. So first let us create the circuit. Okay, we want some transistors from GPDK180, NMOS and PMOS. Okay, so the size is important for this experiment. In the first case, we are going to create a unit inverter. So that is going to be 400 nanometer for the NMOS transistor, and the PMOS transistor is going to be 800 nanometer. So we'll make that change 800N. Okay, and place that, and the load is also going to be a PMOS and NMOS transistor. The reason is we don't know exactly what is the value of the NMOS and PMOS capacitance. So only relative to each other we can find out what is the sizing. So we are going to make the maximum width transistor as the load, which is going to be 50U for the PMOS transistor. Above this it will not take. Suppose we give 60U, right? It will say 60U exceeds the upper limit of 50U. So we have to be satisfied with that, and this is basically going to be our load. Okay, this is not part of the circuit. This is basically inverter chains or buffers are inserted when there is a very high capacitive load to be driven, and this very high capacitive load in our case is going to be the maximum size unit inverter, maximum size inverter, which is 50U for the PMOS transistor and 25U for the NMOS transistor. So make the total with us 25U, and this is coming here. Okay, so then create the inverter circuit, connect the fourth terminals here, connect the fourth terminals here, same in the load side also. Okay, and then okay, place the sources, analog lib, put 1.8. Okay, so one for this and one for this. You can use the same one also, no problem. Just so that the connections look a little more neater, I'm using two separate VDC voltages, but even one is fine. Same thing for ground. I generally like to put more of them so that I don't have wires going across. I can put here one, I can put here one, I can put one here, and I can put one here. Nobody is going to ask me anything. Of course, I will not do this in a real circuit because it will be a lot of extra connections, but this is fine, no problem. And finally I need one V pulse for the input, and the DC voltage is 1.8, and voltage 1 and voltage 2 1.8 and fine. I'm going to make the period little bigger than last time, because for this circuits the load is very big, so 10 nanoseconds period might not be enough sometimes, so we will make it as a 20 nanosecond period, and that input comes to the first. So basically what is the objective of this thing is, the input is something, okay, it will be generated by some other gate, of course, that is be transmitted to the output. That is, it has to come to this point, and the problem is it is going to go through this very big load, and it is going to get delayed. So that connection comes from here to here. That is, the output of this is given as input to this. That is how this input reaches the output. Now this is our circuit. Okay, so let us do a check and save, and we want to calculate the delay between this point and this point. We don't care about this point. Okay, our gate is this, it is responsible for creating the output. What is the delay between input and output? So we just need to do a transient analysis. Choose transient analysis. Let us give as 100N, and outputs to be plotted. Select on design, input here and output here. Okay, and then run it. Got it the this thing, and as you can see, it's significantly bigger than all our FO4 delays, etc., because the load is very high. So the output is taking quite a bit of time to reach the final value, and even quite a bit of time to fall and rise. So once we have this, we can measure the markers, etc. So marker, create a marker horizontal at 0.9 as always. Here also marker, create marker 0.9. Okay, so now leave the first 2 or 3 pulses. Let's be here. So 70.975 minus 70.015. So that is about 70.975 minus 70.015. Okay, about 960 picoseconds for the TP-LH, and TP-HL is 80.4364 minus 80.005. So this is about 431 picoseconds. 431 plus that was about 900 equal to divided by 2. So around 650 picoseconds of delay we are getting for the for the load, and this is quite high. So we want to reduce this delay, and for that I'll go back to the same circuit. Okay, and we will have to add the inverter chain here. So the calculations we discussed in class and also in the lab classes, basically if you do the calculations, you will get a capital F of 62, which is approximately 50U divided by 50U for the output divided by 800 for the input. So capital F will be around 62.2, and with that we can try to do the calculation. So the first thing is how many stages in the inverter chain, and for that we have the okay, so for that we have F equal to let me open a notepad. Okay, so F equal to 62.2, 62.5 I think. So capital N equal to log 62.5 divided by log 3.59. This will give us approximately 3.23 stages, but N cannot be 3.23 stages. Assume N equal to 3, 3 stages, and now we have to have 3 stages in our inverter chain, including the first stage. So first stage sizes are fixed, so there will be a second stage, there will be a third stage, and after that this is the load part. So there will be 2 more inverters that have to be added here. So I will delete this connection for now. Okay, so what we have to decide is what are the sizes of those inverters. Inverter circuit is fixed. If you want, I can draw that now, no problem. Okay, let me add the inverters like we discussed. So just zoom out a little bit. I'll move this up so I have some more space for my circuits, and I will insert the inverters. So it is at NMOS. Okay, one more here and one more here, and similarly PMOS. Okay, so this is our inverter chain, partial nevertheless, not the full chain, but we have some more sizes to enter. These are not the right sizes. Okay, so how do we get the sizes? Let's make the connections also. So the fourth terminal comes here, the fourth terminal comes here, same here, and the inverter connected here, inverter connected like this, and the outputs of one is driving the input of the other. Okay, so which means this output comes here, this output comes here, and finally this output is passed on to the load part. Okay, so this is our circuit now, and the top part connections have to be given to the other two inverters, the bottom part also given to the other two inverters. So this completes the circuit, okay, for the inverter chain, but we don't have the sizes correct yet. So this is 800N, 400N first stage. This is the load stage, the middle two stages. Okay, how do we get the sizes? And for that we have to remember the method of logical effort states that least delay is when GIHI is equal to 62.5, okay, to power 1 by 3, to power 1 by n, and 62.5 has relatively good cube root, which is approximately 4. So hence we choose G1H1 equal to G2H2 equal to G3H3 equal to 4. Okay, this is what is going to give us the sizes. From above, H1 equal to 4. Hence, the second inverter should be 4 times larger to get H equal to C out by C in equal to 4. This is the approximate calculation that we are going to use for the inverter. So once we have this, then it becomes very simple. 800. So this transistor should be 4 times more than 800, and that means it will be 3.2 U. Okay, so we made a mistake. 3.2 U, and that is the size for this one. This one 400, 4 times larger, so that is going to make it 1.6 U. Okay, and the next transistor, okay, in the chain has to be 4 times more than 3.2, not 4 times more than 800. Then you'll be putting 3.2, 3.2. That's not correct. The successive inverter should be 4 times larger than the previous inverter. So the previous inverter was 3.2, means the successive one should be around 12.5 U, and that is what we will put for the PMOS, and the NMOS is approximately always half of the PMOS. So 12.5 means you make it 6.25 U. Okay, and the last stage we cannot put anything because this is the load part, this is fixed. But if you see the multiplication factor G3H3, this will also automatically come to 4. 12.5 into 4 is 50, 6.25 into 4 is 25, and this is basically our inverter chain. Okay, now the rest is the same. We will calculate the delay quickly. We'll remove this. Analysis is fine. These two we will delete. Okay, outputs to be plotted. Select on design. This one, and now the output is not this, not this, this, because this is the output of my inverter chain, not this also. That is the load part. So this is the output of my inverter chain, and we will do the simulation. Separate it. If you see directly, you can see it's much better than last time. Last time it was going like this and it's falling like this. This time it's going up quickly, which means that our delay is going to be lesser. So do the same thing, create markers, and one marker here. Okay, and this time if you calculate, leave the first few pulses. 60.1948 minus 60.005, that is 60.1948 minus 60.005. So you get around 189 picoseconds for the TPHL. TPLH similarly 70.2244 70.2244 minus 70.015 209. So 209 plus around 190 divided by 2. Just 200 picoseconds you will get for the delay. So by adding the inverter chain, okay, we have reduced the delay from around 650 picoseconds to just 200 picoseconds, more than one third, like more than 300% reduction we have got. Now this is the first part of the experiment. If you want to be more adventurous, typically if we have a full lab class for this experiment, we will ask the students to choose different inverter chains. One set of students will choose 4 stages for the inverter chain. In this, okay, we have chosen 3, but instead of 3 you choose 4, and then you will get a different number for GIHI. You will get some other number. It will be maybe slightly lesser than that, maybe 62.2.8, and you put the sizes according to this ratio, calculate the delay. That is one set of students. Another set of students will choose 2, and they will choose square root of 62.5, which is around 8, okay, and there is no G3H3, it's only G2H2. In that case, there was a G4H4 also, sorry. So they will also design a new inverter chain which has only 2 stages. This whole stage will not be there. And again, calculate the delay between the input and the output of the inverter chain. And in both the cases, the delay should be more than 200 picoseconds, because according to the theory, the best stages are chosen when we follow this relation, that is n equal to log 62.5 by log 3.59. But we will not do all that. We will just create it for one and compare it with the previous case when we have no inverter change at all, just the gate driving the output. We got 650, that is the first. Second is this one, and if you compare these two, you should see the reduction in the propagation delay. Okay, so this is the experiment with inverter chains.